Hi, welcome to this video where I'm going to show you how to add probably the most inconvenient situation you could land in physics regarding vectors. It's how to add non-parallel, non-perpendicular vectors. Everything else regarding vectors is generally pretty straightforward. You either can just add them directly to each other, or you can use the so-called Pythagorean theorem to add them by just using a squared plus b squared equals c squared. But in a situation like this, where you don't have vectors at right angles, you don't have vectors that are just already perpendicular or that are already parallel to each other, you have to do a little bit more work to add those mathematically. So what I'm going to do in this video is walk you through kind of a step-by-step process that you should think through as you're approaching a problem like this. So to start with, I like using these pictures here at the top to just give an idea of how these are adding visually. So let's say we have two vectors A and B that are, well, non-perpendicular like this, meaning they're at an acute or an obtuse angle. Well, again, with head to tail method, you're starting with vector A here and moving along, and then from the tip of vector A, you add vector B directly off of that over here. And then your resultant vector, what you get out of it is just the straight line distance from the tail of vector A to the tip of vector B, or from the tail of your first vector to the tip of your final vector. Okay, so visually that's great, and if you had a ruler and a protractor, you could do everything from there. But in this case, assuming we don't have any of that, or we don't have a grid system, and we just have to rely on numbers, how do we add these things together to get that resultant? Well, the answer comes with how we choose to break up these vectors A and B here. Now, if you'll notice, let's just highlight the horizontal part of these vectors. Vector A takes us some distance to the right over here, like that, okay? And then vector B also takes us some distance to the right over here. Now, if we're just looking at horizontal, remember that if you have two vectors that are already going in the same direction, it's perfectly fine to just add them directly to each other, just 2 plus 2 equals 4. So if you notice, what's happened here is how these two vectors, A and B, added together horizontally gives you the horizontal component of our resultant, the purple vector. Okay? And now if you pay attention to the vertical sector, the same thing happens. They add together vertically to give you the vertical component of the resultant. Okay? So that's all happening while we're doing this. And so we're going to walk you through the process of doing this mathematically and getting used to this idea of breaking things into components to add them way easier. Okay, so let's get started. So down here, we have two vectors, A and B, that are not at all related to the ones in the pictures above. So don't let that confuse you. So vector A is the one I'm going to focus on, and then I'll use vector B as a way for you to kind of practice what I just did in the video. So vector A is, it has a magnitude of 32 meters at an angle or a heading of 48 degrees. And to be specific here, if there's no other reference provided, assume that the reference point is from the positive x direction over here, or the positive x-axis. So 32 meters at 48 degrees means it's something like 32 meter long vector this way, and then the angle above the x-axis is 48 degrees. Like that. Now vector B, which I'll do in red, let's say. Oh, there we go. There we go. Oh, there we go. Annoying software. Is 50 meters, so it's going to be longer as an arrow, but it's also at 260 degrees, which is a little rough. So think about your quadrants. Think all the way back to the class where you might have covered this in math. So on a coordinate system like this, we always rotate from 0 to 90 to 180 degrees meaning like if you say somebody has done a complete 180, it means they've like turned around entirely from the direction they were going. That's what that is. And then this next one over here is 270. You're basically going in steps of 90 degrees every time you go through a right angle, which makes sense, all the way back to 360 degrees. So if vector B is at 260 degrees, then visually it's going to be somewhere over here, so like down and to the left. And we'll make it kind of visually longer, but really it's the numbers that matter here. So this angle would go all the way around to 260 degrees, and its magnitude is 50 meters. Okay? So if you want, you could take this and use, like, kind of plop it around with parallelogram method to visually see how these vectors are going to add together. If we were to do that, I'll just kind of eyeball it a little bit. Well, with parallelogram method, it's going to look something like this. Ish. So you should expect our resultant vector by the end of this problem to be from where the solid lines intersect to where the dotted lines intersect. So kind of down and to the right. So if all goes according to the plan, at the end of all of this, our resultant vector should be in the fourth quadrant, or down and to the right, and it looks like it's going to get a little shorter. All right, so use that to check your work at the end. And remember, you're always able to do this. It really helps with checking your work. Kind of a sanity check of sorts. Okay, so step one. So for step one, really the first thing that we did over here visually was break vector A and B into horizontal and vertical components. So I'm going to find the vertical and horizontal components of vector A, and then I will have you pause and find the components for vector B before we move on. Okay? So for vector A, I'm going to go over here. And when you're finding the components of a vector just numerically, that means all you really need is the magnitude of the vector and the angle that it's at. That's it. And if you need a bit of a recap, then up here, say you're given like the hypotenuse or the magnitude of some vector, and you're given the angle that it's at. Well, the equation you're using is really just sine, cosine, or tangent, and the relationship that follows with that. So for instance, for horizontal, you would say that if you want to find the horizontal component, you'd say cosine theta is equal to adjacent over hypotenuse. And so then using our triangle over here as a reference, well, Vx is our adjacent, and V, our given velocity, is the hypotenuse. So we can then substitute those in over here. And then at that point, you solve. So here, I'll move out of the way. There we go. You just multiply both sides by the magnitude of the vector, velocity, V, to solve for Vx. That's it. And 9 times out of 10, you can always assume that the horizontal component of a vector is going to be related to cosine, and the vertical component will be related to sine of the angle. I say 9 times out of 10 because it will not always be the case. Sometimes, if I'm feeling a little devious, I'll give you an angle with respect to a vertical, like so with respect to the y-axis as opposed to x, in which case the trig is going to be flipped around. So if I would say, just word to the wise, always check by drawing a picture to make sure that everything's in the right place. Okay, so then down here, for the x component, so I'm going to say, well, what do we want to call this? I'll call this ax and ay equals, and ay equals. Well, ax is going to equal the magnitude of a, so that's going to be, well, I'll just write out the equation first. So a times cosine of theta a, let's call it. And so that's going to equal 32 meters times cosine of 48 degrees. So if you check your calculator here, that should give you about a magnitude of 21 point, let's just call that 21. Keep our sig figs simple. So 21 meters. Okay. Now let's do the same thing for y. Now remember, in this case, vertical is generally associated with sine of theta. So it'll be a times sine of theta a. And that's going to equal 32 times sine of 48 degrees. And that should give you about a magnitude of 24 meters if you run that through your calculator. If you're not getting these numbers and you ran them through your calculator, make sure that your calculator's in degrees. Math teachers love radians, and so you're going to be doing a lot of switching back and forth between degrees in physics and radians in math, especially if you're in pre-cal. So keep that in mind. Okay, so now that we have this, I'm going to do a little squiggle here. And so over here, for vector b, I want you to do the exact same thing with these numbers here. So we'll just go ahead and set that out. So bx and by. And so I want you to pause and try this out on your own, and then we'll convene after the break. See you soon. All right, welcome back. I've gone ahead and put the remaining work for bx and by over here so you can check and make sure you got it. Now you'll notice something kind of cool happened here if you held true to the 260-degree angle when you plugged it in, which is that calculators, while they can be silly most of the time, they are pretty smart if you plug in an angle from 0 to 360 degrees. Because when you do this, what you'll find is that it will output not only the correct magnitude for the component vector, but also the correct direction, which is super handy because it means even if you didn't draw this picture over here, it will correctly tell you that this vector, b, should be made up of two components that go down and to the left, respectively. So know that this is an advantage of sticking to the 0 through 360-degree angle system, which is that you typically don't have to worry about drawing a picture to make sure that your components are going in the right direction. Okay, so with that, we're going to move on to step 2. Yeah, right, that was all step 1. Step 2 and onwards get a lot faster, so the hard work is done. So step 2 is to add the horizontal components together. Again, kind of like what we did over here visually. Because now what we've got is AX and BX that both are going in the same, are going along the same axis. AX is going to the right and BX is going to the left. So at this point, it's kind of just a tug of war between those two vectors. So what you want to do now is, since you've got them all on the same page or on the same axis technically, step 2 is to add the horizontal components together. So I'll go ahead and just say that that's what I'm doing here. Components. And this step is pretty easy, at least as long as you're comfortable with addition, or subtraction in this case, which is that your resultant, which I'm going to call vector r. Oh, whoops. Gosh, yeah. Drawboard is silly. I'm going to call our resultant vector r over here. And so I'm going to say the x component of our resultant, rx, equals ax plus bx. That's it. Because they're all on the same axis now, there's not even any Pythagorean that we have to do yet. So ax plus bx is going to be 21 meters plus -9 meters. Remember, we're always adding, even when we're really subtracting, in effect. So you should get a total x component of 12 meters, and I'm going to indicate that its direction is to the right, just so we can keep that in mind. Or you could just say that it's positive 12. Either way, it's fine. All right, and that's our resultant x. So now again, step 3 is the same thing, but for the vertical direction. So we're going to add the vertical components. and I want you to do this step. So now just keep in mind, we're going to call this ry, and it's going to equal, well, I'll let you figure it out. So we'll pause again, work this out on your own, and then come back, and we will move on from here. See you soon. Welcome back. All right, so if you did everything all right, you should have gotten a total vertical component for your resultant of negative 25 meters. Now we can go check our picture that we sketched at the beginning, and yeah, that tracks. So we've got something that's going down, negative 25 down, and to the right, positive 12 to the right. So everything seems to be looking pretty good so far. So step 4 is now where we implement the so-called Pythagorean theorem. So what we have now is, I'm just going to draw it. We have our vector r that looks something like this. We've got 12 meters to the right, and we've got 25 meters down. Negative 25 meters. So our resultant vector now looks like this, as opposed to the crazy non-perpendicular, non-parallel, blah, blah, blah mess that we had at the start. This is much nicer looking because, get this, we've now created a right triangle. So by choosing wisely the horizontal and vertical components, that's what we're trying to aim for at the end of the day, is we're trying to pick two vectors that are perpendicular to each other, so we can kind of force this problem's hand and give us a right triangle. Again, we love right triangles out here. So step 4 is to use these two components, rx and ry, to get our overall resultant, or the magnitude of our resultant, which is r. So over here, we can now get that by using the so-called Pythagorean theorem, which states that the magnitude of r squared is equal to the magnitude of rx squared plus the magnitude of ry squared. And again, this only works because they are at right angles to each other. So then we really just want to square root both sides to get them both to solve for r itself. And so r is going to equal the square root of 12 squared plus negative 25 squared. And you might be wondering, why the heck are you writing those parentheses there? That just seems like you're burning a lot of extra calories writing those. I do it because I want to force my calculator's hand in making sure that it is solving for the exact thing that I want. And if you want to see what I mean, well, if you plug this into your calculator, you're going to get the right answer, which is 5 squared plus 12 squared, and then you take the square root of that. Oh, 769, whoop, which is about 28 meters. Now, what I want you to do is maybe pause and try to enter this without those parentheses. You're going to find that your calculator misinterprets the negative sign right here, because it's going to apply that negative sign after squaring 25, which means it's going to be 12. It's going to interpret this and go through the math as 12 squared minus 25 squared, which is going to probably give you an imaginary number here, which we're never going to have in this class. So again, I love calculators. They're very handy, but they can totally misinterpret what you want from them sometimes. So use parentheses. They are your best friend and can save you from a lot of math trouble. Okay, so we now have how long our resultant vector is, but we still don't really know what angle it's at. It could be going in any direction, wherever. So what we need to do now is figure out the angle, which I'm going to just draw to our existing picture here. And let's say that we want to find it below the x-axis, like over here. Okay? So then, in order to do this, generally, if you have the component vectors set up, the angle that your vector r is at is going to involve the inverse tangent, so tan to the -1, of the opposite over the adjacent. So in this case, your opposite to the angle is 25, -25 technically. So again, I'm going to use parentheses here. So I'm going to say -25 divided by +12. And you probably won't be able to enter the positive into your calculator, but the negative is important. And again, I want you to use parentheses when you're doing this, especially if you don't just want to throw out the negative sign altogether, because this is what's going to help your calculator understand exactly which value is negative and which one is positive. Otherwise, it's not really going to know, and it's just going to throw out a guess. So if you do this, tan -1, -25 divided by +12, it should give you an angle, and this is kind of annoying, of -64 point, we'll just call that -64 degrees. Now, you're going to see that negative angle and you're going to be like, huh, okay, interesting. What is that? That's really just telling us that we're rotating this angle down from the x-axis. So if you wanted to really figure out kind of where this thing is at, what you could do is add this value to 360 degrees. So you could do 360 plus -64. And so your real angle is 296 degrees. If you're going like all the way around to where we kind of stated it would be at the start. All right. There are a couple of other ways you could do that. You could say, well, this is 64 degrees. Well, if you drew the picture here, then honestly, as far as like a test goes, if I'm asking you to solve for something like this, I would be okay with you having the picture and then just the angle that you solved for outright over here. On things like Quest, when they're specifying a specific coordinate system to answer within, though, you're going to have to maybe adjust your answer a little bit. But you could also say this was like -64 degrees below the positive x-axis or something. Or maybe south of east would be fine as well. Okay, so that was all a very involved process, but that's really the worst that these sorts of vectors can really get. There isn't really anything worse other than adding an extra dimension, like a third dimension, so the z direction. Or, as you're going to find on quest problem number 12 in your homework, which has you do this exact same process, but with not 2, but 3 vectors. So just keep in mind that the process is totally the same. It's just that you're going to be adding 3 components to each other as opposed to 2. And then everything else will remain the same. So it's a little tedious, but that's how it's done. All right, so thank you for watching my video. And if you enjoyed this, hopefully there'll be more to come. Peace.